All right, so for our research project, we researched the hydrogenation of unsaturated compounds. Our main two focuses were limonene and alpha-phellandrene. Limonene is found in the peels of citrus fruits, and alpha-phellandrene is found in oils, essential oils such as eucalyptus. Moving forward to our purpose, we want to remove the double bonds in limonene. This process is called hydrogenation. As you can see, there is a double bond on the isopropyl group and inside the cyclohexane. We want to transform this molecule into one isopropyl 4-methyl cyclohexane. Moving on to alpha-phellandrene, we have the same concept. We want to remove the double bonds. However, in alpha-phellandrene, there are two double bonds inside the cyclohexane, and there is not one present on the isopropyl group. Again, we are trying to transform it into the same molecule, one isopropyl 4-methyl cyclohexane.
So the materials and the procedure went as follows. So we had the chemicals limonene and alpha-phellandrene, glacial acetic acid, palladium, which is the metal that acts as our catalyst, hydrogen gas and deuterium gas, hexanes, magnesium sulfate to absorb the water, and deuterated acetone for the NMR. So first we placed 10 milliliters of limonene or alpha-phellandrene into the reaction vessel, and then about 0.2 grams of palladium, again, which is our metal, which acts as catalyst, and then 25 milliliters of glacial acetic acid. So we put the reaction vessel into the hydrogenation apparatus for 1 hour under 20 psi and 25 degrees Celsius for the temperature and pressure settings. Next, we vacuum filtrated it after the hydrogenation in order to remove most of the palladium. And then we placed into the set funnel with about 20 milliliters of distilled water and 10 milliliters of hexanes. And we poured and we extracted it twice in order to keep the organic layer. Then we added about 3 to 4 scoops of anhydrous magnesium sulfate in order to absorb all the excess water. And then performed vacuum filtration in order to get our product. Next, we performed a Rotovap in order to remove all of the hexanes. So we set it at about 60 degrees Celsius, which is 10 degrees Celsius lower than the boiling point of the hexanes. After this, we obtained an IR in order to see what our product looks like with the peaks after having the hydrogenation. And then finally an NMR, so we placed a few drops of the product into a sample tube, and we filled the tube about a third of a way with our solvent, which was deuterated acetone.
So the first product, we decided to take an IR and NMR of both, but we'll talk about limonene first. So we wanted baseline data to be able to compare our final results to. So we took an IR of the pure product, which indicates a peak above 3,000, which lets us know that there are alkenes present, which means double bonds. And our NMR shows 2 important peaks. There are obviously more than 2, but the only 2 that we focused on were peak A, which indicates that there's only 1 hydrogen off of that double bond rather than 2, which would mean that it was saturated in alkane. And the same goes for peak B, which shows 2 hydrogens off of the double bond, which, typically would be 3 if it was saturated and didn't have a double bond there. And our results that we compared to that baseline data, the numbers aren't that important, but the trend is what's important. So the pressure decreased and the temperature had an overall increase and then decreased at the end, which is important. We'll talk about that later. That is ultimately what we wanted to see. And our IR of the product has no peak anymore above 3,000, which was the goal because that now indicates that it's all saturated alkanes. There are no more double bonds. The NMR, the peaks that are important would be peak C, which now shows, as we said before, 3 rather than 2 hydrogens. And peak B is also important because previously, since there was a double bond that attached to that carbon, there were already 4 bonds, so there would be no hydrogen. However, once we removed that double bond, now it turns into only 3 bonds to that carbon, so now there has to be a hydrogen present.
So the interpretation of all this data and what this essentially means is that because there was a decrease in pressure and an increase in temperature during the hydrogenation, it shows that our bonds were breaking. And then the IR spectra showed no peaks above 3,000, which means we only had saturated alkanes or single bonds. And we verified all of our structures using the NMR.
Transitioning into our alpha-phellandrene data, we again took a baseline to compare to our product. There is a peak above 3,000, which indicates that double bond, as Jenna was saying, an alkene. And then in the NMR, we drew the structure, and there is 1 hydrogen present throughout the cyclohexane on those double bonds, and that's indicated by peak A. Peak B and C there are just indicated just to show the hydrogens, but our main peak that we focused on was A due to the single hydrogen, and when those double bonds are removed, we should have 2 hydrogens present where peak A is. Moving forward to our results. First, the table, you can see there is a decrease in pressure and an increase in temperature followed by a decrease. Again, we'll get to what that means later, and we already touched upon it a little bit. Moving forward, our IR of the product of the alpha-phellandrene, there is no peaks above 3,000, which indicates we have all saturated alkanes. The double bonds were in fact broke. Moving on to the NMR. Peak F here is one of the main peaks we want to look at. There's 2 hydrogens present there. Peak F indicates that all the double bonds were in fact broke, and we have 2 hydrogens present throughout the whole cyclohexane. Peak B is another peak hydrogen signal that we want to touch upon because there is a new hydrogen present here as well. Before it was a sp3 hybridized, and now there is a hydrogen there instead of the double bond.
So again, what does this all mean? So during the hydrogenation, we once again had a decrease in pressure and an increase in temperature, which showed that all of the bonds were breaking. And that shows that both the bonds in the cyclohexane broke, and the IR spectra showed that we only have saturated alkanes. It showed that our hydrogenating of limonene and alpha-phellandrene was successful because we removed all of the double bonds and verified using the IR and NMR, and then we repeated our results 2 weeks in a row, and we got roughly the same.
So for the first part of the experiment, we were using hydrogen gas trying to break the double bonds, but at the tail end of our time doing research, we wanted to experiment with deuterium, which is essentially a hydrogen with an extra neutron. The results showed roughly the same trend of a decrease in pressure, increase in temperature, and then that slight decrease at the end there. And the IR had the same thing that we anticipated of all peaks below 3,000 afterward, indicating all saturated alkanes, all the double bonds were broken, which is what we wanted. The NMR, we labeled all of the peaks here, but the only ones that are truly important would be peak B and peak A, which indicate that the previously sp2 hybridized carbon right there is now sp3 because it did have a double bond, but now it has that hydrogen because we broke the double bond. And same goes for peak A. And peak C indicates that there are 3 hydrogens coming off of that carbon, where before, when there was a double bond there were only 2. The alpha-phellandrene has that same trend, again, that we wanted to see of the decrease in pressure, increase, and then slight decrease of temperature, indicating the double bonds breaking. The The IR has the same deal, which is what we want since we were trying to obtain the exact same product as before. And same with the NMR, which I will not mention the peaks since it is identical to the other one, but the A, B, and C is less relevant for alpha-phelandrene since all the peaks were inside of the cyclohexane, but A and B are pretty relevant here. It's just the main point is that we obtained the exact same spectra.
Moving forward, our interpretation of all this data, similar as before, the decrease in pressure, increase in temperature means we did break these bonds. However, this time it is with the deuterium gas. We do have all saturated alkanes, and we did verify our structures with the NMR with the deuterium gas. In conclusion, we were unsure if we were successful with the deuterium gas. The deuterium gas is fairly invisible on the spectral data because it appears so similar to a hydrogen. The splitting does appear different to the hydrogen, but the peaks were in the same place, and that's how we were able to label our final NMRs with the structures. We do believe we were successful. However, we could not replicate our results due to our lack of time in the end of the semester. But if we had more time moving forward in the future, that is what we want to do, is to try to replicate our results and of the limonene and alpha-phelandrene with the deuterated gas. However, one thing that we can say is that our IR structures did indicate that all the double bonds were broke. So after one trial, we would like to say that we were successful in doing so. And then, do you guys have any questions?